I'd like to finish off this section by just looking over a couple quick results that have to do with eigenvalues. So let's consider a triangular matrix. If T is a triangular matrix, either upper triangular or lower triangular, then the eigenvalues of T are just the entries on the main diagonal. Now, I'm not going to do a formal proof, but it's pretty easy to see if you just take an example. So let's do 1, 2, 3, 0, 4, 5, 0, 0, 6. This is an upper triangular matrix. All right. So if I look at the characteristic equation of this matrix, let's see what we get here. We would get the determinant of 1 minus lambda, 2, 3, 0, 4 minus lambda, 5, 0, 0, 6 minus lambda. But this is a triangular matrix. And what do we know about the determinants of triangular matrices? The term is just the product of the entries along the main diagonal. This is just going to be 1 minus lambda, 4 minus lambda, 6 minus lambda. Okay? Product of the entries along the main diagonal. Setting that equal to 0, the only way that happens is if either lambda equals 1, or looking at the second factor here, lambda equals 4, or the last factor, lambda equals 6. And those are exactly the entries along the main diagonal. All right? So this is just an example, but it's illustrative of why this is true generally. If you have a triangular matrix, your eigenvalues are just the values along the main diagonal. And because it's true for triangular matrices, it's clearly true for diagonal matrices. If D is a diagonal matrix, then the eigenvalues of D are the entries along the main diagonal also. And the reason, of course, is that a diagonal matrix is just a special kind of triangular matrix, right? It's a matrix that's both upper triangular and also lower triangular. And then the final result I wanted to cover is that if we have a square matrix, it has an eigenvalue of 0 if and only if that matrix is singular. So this one we will prove, but it's a quick proof. Observe matrix A is singular if and only if the determinant of A is equal to 0. But the determinant of A is equal to the determinant of A minus 0i. Notice that means 0, meaning 0 is a solution to the characteristic equation. To the characteristic equation if and only if A is singular. Okay? If this is equal to 0, as these two equations suggest, then 0 is in a solution of the characteristic equation and therefore an eigenvalue of the system, right? If you're a solution of the characteristic equation, then you're an eigenvalue. And so singular matrices, non-invertible matrices, they have an eigenvalue of 0, and if a matrix has an eigenvalue of 0, then it is a singular matrix.